Hello all. This is Team62's presentation for their Global Emergency Autonomous Response System prototype, or GEARS. Team 62 was tasked with constructing a robot that was capable of accomplishing 5 tasks: precise navigation through damaged areas, transportation of a piece of cargo designed by the team through unknown territory to a community on the other side, characterization and avoidance of hazardous locations within the area, transmittance of a map of the path taken throughout the environment, and an indication of the contents of the cargo using a method not tied to any specific language or culture, and communication with community recipients in a non hostile manner. In the final presentation, the precise navigation through damaged areas will be simulated by a maze. Additionally, the robot will have to characterize, log, and track the location of 2 hazards: IR radiation and magnets. Lastly, the robot will have to be able to track its location throughout the maze, as well as the location of the hazards, and output a map of these 2 things.
This project was requested by LP Harris Technologies, Joint Robotic Solutions and Disaster Response, for use in global disaster response, both natural and man-made. The prototype developed by the team poses incredible use to world governmental organizations like FEMA in order to supply aid to their citizens. Additionally, the prototype developed by the team is useful to world humanitarian and aid organizations like the Red Cross or Red Crescent and UNICEF. The team met every day after engineering class for an hour, while Thomas and Jack met every day to work on the code and testing. The team had to redevelop a Gantt chart different from the one developed for the presentation of competency, which we'll see on the next slide. In addition to the Gantt chart, the team developed a work breakdown structure to further subdivide the work. In order to manage the code, the team developed a flow chart, which we'll be seeing later. This is our Gantt chart. The team used this Gantt chart to determine the resources we needed and to plan the order in which we completed our tasks. The team stuck very closely with this throughout the semester and proved to be quite successful. Team 62 created its work breakdown structure in order to visualize the required components and subcomponents required for the success of the robot, as desired by L.P. Harris. The team recognized the utmost importance of meeting the customer needs and decided to assemble a list of all relevant and possible customer needs. The team took these needs and turned them into technical requirements, as seen in the second column. The team quantified these technical requirements into technical needs and target values. The prototype achieved values experienced during testing is in the last column. On the second row, the customer need is transport desired cargo through unknown terrain to a community on the other side. The technical need for this customer need is successful path generation through the maze. The technical requirement for this need is gears successfully generates a danger-free path through the maze 95% of the time, and the target value is gears successfully generates a danger-free path through the maze 97% of the time. On the third row, the customer need is to characterize hazardous locations in the area. Technical need for this customer need is detection of IR beacon and strong magnets with relative strength. The technical requirement for this need is gears can successfully detect 90% of the hazards within an area, and the target value is gears can successfully detect 98% of the hazards within an area. On the fourth row, the customer need is transmits a map of hazardous locations with other pertinent information. The technical need is saves and characterizes detected hazardous locations. The technical requirement for this need is gear successfully accesses the relative strength and types of hazards 95% of the time, and the target value is gear successfully accesses the relative strength and types of hazard 100% of the time. On the fifth row, the customer need is to transmit a map of the path taken through the environment. The technical need is accurate map generation. The technical requirement for this need is gear successfully replicates a map of the maze 95% of the time, and the target value is gear successfully replicates a map of its path 99% of the time. On the fifth row and the last row, the customer needs is indicate contents of cargo using a method not tied to any specific language or culture. And the technical need for this customer need is symbolic representation of cargo. And the technical requirement for this need is 95% of randomly selected individuals can understand contents of the cargo container. And the target value is 100% of randomly selected individuals can understand the contents of the cargo container.
The team adhered to a strict design process in order to ensure that the right steps were being taken in the creation of the gears, as well as ensuring that these steps were being taken in the right order. Team 62 referred to the design process as introduced in the course ENGR162 with the steps as follows. Define the problem to be solved, acquire and assemble pertinent data, identify solutions, constraints, and criteria, develop alternative solutions, select a solution based on the analysis of the alternatives, and then communicate those results. In order to make the decisions that we did, Team 62 utilized brainstorming methods, most notably prior art. The team frequently referred to real-life rovers and prior robotic projects to take ideas from, and that was all and to consider many options for all of the required systems for this robot. After doing some testing of various cargo, sensor, and drivetrain systems, a weighted decision matrix was made to identify the optimal combination of systems. From this point, the team had a more refined idea of what systems were going to be utilized on the final gears prototype. An example of the decision matrix is shown on this slide. So to conclude, the final design of the robot featured an angled two-wheel drive frame with differential turning in the back. It had front-mounted sensors with 2 ultrasonics, an IMU, an infrared sensor, 1 gyro, and 2 touch sensors to start and stop the code. It had a conveyored cargo system below the Raspberry Pi, as well as a frontal design featuring low-friction skis to allow for ease of turning. And overall, there's features for the modularity and ease of use. So those touch sensors for running and stopping the code, as I described, as well as the battery mount, as you can see there in the back of the robot.
Alright, so before I get into the code logic itself, I do want to talk about some of the decisions we made when we were working to implement the code. Most of our decision making was based on first brainstorming a lot of ideas at the beginning of the process, and then later testing out a lot of different ideas to see what would work. The first main thing I want to talk about is the way that we tracked our angle and position, which were important for mapping. We initially brainstormed 3 main ideas. We were going to originally use the IMU's acceleration and angular velocity functions, but the values ended up being extremely inaccurate and required using some integration that we weren't able to do due to the fact that the robot's processing speed was unknown. We eventually found that the motor encoders, that is, the actual amount of distance that the motor itself has moved over time, ended up working really well for telling us how far our robot had moved. We originally were going to use this for turning as well, but then we found out that the standalone gyro sensor, shown in the bottom right, ended up being very accurate for measuring angles. We eventually switched to motor encoders after discovering how useful they were for position tracking, but in the end we ended up using the gyro sensor because it was the most accurate. For ultrasonic sensors, we had a few different ideas about how exactly we were going to install the ultrasonic sensors on our robot. We were going to think about doing just a front sensor, just a right sensor, doing front right and left, or perhaps front and left, or maybe front and right, which is what we decided on. The reason we decided on front and right has to do with the right wall rule, which I will talk about in more detail later. To simplify the code, we chose to not also implement a left sensor. Now let me talk about the foundations of the code, which is the basic functions corresponding to the motors and sensors. These allowed us to interface with the motors and sensors with various BrickPy and GovePy commands. Most of them are relatively simple. As you can see on the right, the infrared sensor, which was a new sensor we added this semester, is a very simple function that simply takes the 2 values from the GovePy and returns the larger of the 2 values. The IMU sensor was a little bit more complicated because it required using various filtering functions that were provided by the instructional team. Next, I want to talk about the meat of the code, which is the right wall rule maze navigation. Although this is, of course, the simplest maze navigation, and that's the reason we chose it, it is still very complicated to implement directly in code, hence the large flowchart on the right. For left turns, it's pretty simple. We were able to just see when there was a corner using both sensors and then turn left. However, for right turns, it's a bit more complicated. because when it sees that there is no right wall and it needs to turn, it first needs to align itself so it can turn. So there are two different ways it can align itself. The first is by seeing a wall in front of it, which it will see using the same front threshold as for the left turns, or when it sees a right wall, that is when it's gone past in a T intersection, then it needs to back up a little bit and turn. We had it do both of these things and it ended up navigating the maze very well. And the bottom diagram shows the sensor thresholds that we chose, which were based on a lot of experimentation and determining what worked best to cause the robots not to run into the walls, but also not be too far from them that the turns swung them into the opposite wall. I want to quickly talk about a technical thing that we implemented for some of our code, which is proportional control. We did not use the full PID because we didn't want to overcomplicate the code, and the proportional control was particularly already effective. There are two places in which we implemented proportional control. The first is for turning 90 degrees. We originally were going to just use motor encoders to do this, as I said, but eventually we found the gyro was going to work best, and so to prevent it from overshooting when it read the gyro, we used proportional control such that the motor would start to slow down as the difference between the current angle and the target angle got smaller. The flowchart for this algorithm is shown on the right side. It's fairly linear, but it does use a little bit of looping logic in order to continue reading the values until the target is reached. Detail about. So for the avoidance of the two main types of hazards, which were heat and magnets, we read each of the two sensors using the functions I discussed earlier, and then we simply used thresholds, which were determined experimentally that we felt were useful in locating the sensors from far enough distance without having any false positives. And then it would update the map when it saw the threshold about the value, and then it would just do a 180 and continue on. Another thing is the map generation, which just used a couple of different arrays. You'll see the IR data and the IMU data on the right, which was about the hazard data. Those were updated when the hazards were seen. And then after every step, every time it ran through the function, it would then also check its position, and then if that position was in a new area of the map, it would update the map accordingly. And then a separate function was used at the end so that it wasn't interfering during the robot to make it slower. At the end of the process, a separate function is used to convert all of the data from the arrays into a CSV. The final thing I want to quickly talk about is the drop-off process, which simply used repetition logic to cause the robot to shake quickly, and then later used the same repetition logic in order to communicate friendliness using a small dancing motion. All right, I think that's pretty much everything I'm going to talk about the software.
As for the strengths and weaknesses of our team's prototype, the team believes that the robot excelled in the areas of detection and avoidance, mapping, cargo delivery, and maze navigation, while the robot had consistent weaknesses in its cargo load capacity, communication, hazard characterization, and turning. The team was incredibly impressed by the gear's performance during the final demonstration. The prototype was able to output a map of the hazards it detected, as well as a semi-accurate map of the path it took throughout the maze and the location of the hazards. Although it took a bit of tweaking by the team, the robot was able to turn with an appropriate radius through the maze and reach most of the checkpoints. It was, however, unable to escape the maze. The prototype was accurately able to avoid the IR beacon, and the prototype navigated the maze with a relatively high accuracy, although it wasn't able to escape the maze due to the magnet. Lastly, the prototype was able to drop off the cargo successfully. The prototype, though, was unable to avoid the magnet in the maze. If the team were able to go back and fix their Gears prototype, they would focus on the following systems: IMU filtration, PID control, new mapping code, larger cargo bay, and fixing the cargo conveyor belt. The team would firstly spend more time experimenting with the IMU filtration and the filters that they integrated, and specifically spend more time looking at the parameter values for the dynamic window filter and the reverse Gaussian filter in order to make the magnetic detection and avoidance code more accurate. If given more time, the team would have also liked to experiment with the Kalman code that was given to us. Secondly, the team would go back and fix the mapping code to more accurately track the robot's position throughout the maze, as it did not generate a super accurate map of the maze during the final demonstration. The team would also like to rework the cargo's conveyor belt such that the robot would not have to shake back and forth in order to deliver the cargo. Lastly, the team would like to attempt to model the strength of both the IR and magnetic beacons at distances and how they change over these distances in order to more accurately predict the relative strengths of the respective beacon.